Hello Math 125 students. I'm going to continue to make little videos to go with the test preps. So this week we had a test prep on 6.4 and 6.5. So let's talk about those problems, maybe glance at some old exams that are similar. 6.4 was on work, and there's a lot to be said there. I have several other videos, so I'll try to be minimal and not rehash everything. And then we have average value. So we'll do the last page on that. So this is I grabbed a few kind of more basic problems so that we could get the main idea. So the first one's one of these cable problems. 30-meter cable with a density this is hanging over the side of a tall building. How much work is done in lifting the cable to the top of the building? There are two perspectives on these problems, but I'm going to give you the one that I've always used. So I think of it as a stack of books problem. Now there is another way, but for a stack of books problem, I draw the start, I draw the end, and then I will illustrate those. So we have, it starts hanging all the way down, it ends with it coiled up at the top, and it's 30 meters, and they told us the density here. And it is in kilograms, so we're going to have to multiply it by 9.8. So there's several little things as I mentioned. So the stack of books approach to a work problem, we're trying to do force times distance, and we're trying to find a pattern. But the stack of books approach is this. Let's break this up into a bunch of subdivisions, and let's just look at one of them and see if we can find a pattern. So what we're doing is we're turning the problem into this problem. If I have a book that's right here, and I know how much it weighs, and I'm lifting it to the top, that's the distance lifted. And then the other question we have to figure out is what the force is. And then we're going to do it again for every other slice. This is the stack of books approach. So it's different than the leaky bucket where it's just one object that's getting lighter or heavier. We have a whole bunch of these. There's one here. There's one here. So we're taking different slices of the rope. So if you're taking this perspective, then what happens is the following. You say, well, if I have a slice of thickness delta x, so delta x meters is the thickness of a slice, what's the force? Well, the force is going to be 1 over 4.9 kilograms per meter, because they told me that. I'm going to multiply by 9.8 because of the kilograms. That turns it into newtons. I'm going to multiply by delta x. That should make sense. You know, if you had a segment of rope that was 3 meters long, you want to know how much it weighed, you would do 3 times this times 9.8. But in this case, we don't know the length. It's what we're calling delta x. That represents the force. Now, if you're approaching it as a leaky bucket problem, it's a different perspective. The next thing is we need to figure out how far it's lifted. And you'll notice I haven't labeled anything yet. So because of the way the problem is presented and because we're going all the way to the top, I feel like I'd like to label the top 0. I know that's unusual, but if I label the top 0, then the bottom could be labeled 30. And in this labeling, you know, I'll just do an example. When you're 10 units down, x is 10. So that makes it a little bit nicer. So in this labeling, the distance lifted is just x. If you labeled it the other way, where the bottom was 0 and the top was 30, then x equals 10 would be the same as y equals 20. And in order to get the distance lifted, you'd have to do 30 minus y. That's also correct. Either way, every single slice made it to the top, meaning the one that's at, so I'm going to label the bottom 30 and the top 0. So if you take a slice at 30, it makes it all the way to the top. If you slice at 2, and the problem said it all made it to the top. So this is going to be the integral. I want to do distance times the weight. Now this ends up just being 2 delta x. So times 2 delta x. That's the force in newtons. That's the distance. And then we're integrating this from 0 to 30. So dx. So when you integrate, it just ends up being x squared because the 2 cancels. You get 0 to 30. You get 900. That's it. You know, one way to up the challenge is what happens if it only gets lifted halfway to the top. That's a common one that really messes people up. But the truth is, you can basically then treat it as two problems. You could treat it as the 15 meters. And the question didn't ask this. The 15 meters of rope that did make it to the top is the exact same as what we just did. It's going to be the integral from 0 to 15 of x times 2 dx. But that ignores the rest of the work that was done, which was the work to lift the rest of the rope. We talked about this in class, how if I was doing this, I wouldn't try to incorporate that in integral. I would just say, well, this entire part of the rope all got lifted 15 meters. It all got lifted the same amount. So I can just add 15 meters times however much that part of rope weighs. You might say, well, I don't know what that is. We do. It's 2 newtons and the length per meter. And the length is 15 meters. So this would be the distance. This would be the length. There we go. That would be halfway. Okay, so then we have a pumping problem. A portion of the graph has been rotated around, so there's a bit of drawing. And these should feel, there are similarities to volume revolution in that you're having to label. But how we're using that information is a little different. So I'm drawing a line, y equals 3x, x equals 0 to 1. If this is 1, then this is 3. I didn't draw it very accurately. But it says you have this container. We're rotating around the y-axis. And so it's a cone, if you can picture that. That would have been a better drawing. Anyways, the container is full of a liquid that has a certain density. Find the work required to pump all the liquid out of the side. Now, since it's in pounds and feet, I don't have to multiply by 9.8. It already includes a force. So at this point, here's what we do. We think of it, and this is why I do this question up here this way, because we're going to think about it the exact same way. We're going to think about it as a stack of books. Now, what do I mean by that? So let's do the exact same game. If we take a slice at this level, there are two questions. How far will it be lifted? And how much does it weigh? That's the pattern we need to find. Because of that, you're forced into using the variable y here. You don't get a choice because you need to describe all the things that are at the same height. And so your first thought should be, hey, that looks like a disc. Okay, and you have to label it y because we're talking about, we already gave us an equation, and that's what y represents. So now I'm ready to go. It's going to be the integral. It starts full, so it's going to be integral from 0 to 3 dy. And then for any y, I would like to figure out how much that slice weighs and how far it's lifted. Now the lifted part's easier because you're going to lift it to the top of the container. And so that's going to be just 3 minus y. And here you didn't have a choice of how to label it because it was already given to you. Anyways, and now we need the force. How much does that weigh? Well, the volume of this would be delta y times pi r squared, r being the radius from here to here. So that's the volume. So if we did, here's the delta y, here's the pi times the radius squared, and we forgot to do the 90, so I'll put the 90 in there. And you can use the units to kind of help you. Here is feet. Here is pounds per cubic feet. Here is feet. And then this area is going to be square feet. So the cubic feet and the cubic feet here is going to cancel. So it's going to be foot pounds, which is good. There's going to be a pounds from here and a foot from here. That's a small little double check. If the units don't come out, that something's really wrong. So we're down to basically one last thing, which is what is the pattern for the radius? What is this? How do we label that? We label that in terms of y by solving 1/3 y. So it's these same kind of small skills that are coming up over and over again. Then we're done. Let's factor out the 90 pi. If it was me, I would also factor out the 1/9 after you square. That's going to be 10 pi from 0 to 3. And it's typically worth your while to simplify as much as possible before you integrate. So I would keep going. This is going to be the integral from 0 to 3 of 3y squared minus y cubed dy. So it's going to be 10 pi. And there's going to be a y cubed minus 1/4 y to the 4th from 0 to 3. When I plug in 0, everything's going to be 0. And so it's going to be 10 pi 27 minus 81 over 4. So if I multiply the top and bottom by 4, what is that? Doubling this is 54. So 108. So it's going to be 10 pi 108 over 4 minus 81 over 4. And this is going to be, and you could use a calculator. I just, in these videos, you can see I don't like to pull one out. Okay, so this is going to be 27. And then I can simplify this, 2 and a 5. And then whatever 27 times 5 is, 5, 3, 135. So it's going to be 135 pi over 2. Now let's check those two things. So I got 900 joules for this one. And I got 135 pi over 2 foot-pounds. And this was spring 2016. Spring 2016. So I have to pull this up just in case I did it. Because if I have a typo in the video, I get lots of emails. Again, the videos are about ideas, but I do want to have it right. So there you can see I worked it out both ways with both labelings. 135 pi over 2. Yay! Same thing. All right, so let's go back and keep going. So I'm hoping you can use these to sort of go through and review or clarify a few things or just give you more examples. And also these are straight from old tests, so it's a chance for you to think about this. So a well is in the shape of a cylinder of radius 2 and depth 10. Cylinder, radius 2, depth 10. And it starts half full. Okay, so this is the picture at the start. Find the work required to pump all the water up and out of the well. So at the end it's going to be empty. And these pumping problems, this is not as helpful as it is in the cable problems, but this is what the picture is going to look like at the end. There's going to be nothing in there. Okay. So this is, again, the stack of books approach. So we're going to say, and here you could use X or Y because nothing has been given to you. But let's use, I kind of tell students to use Y always for pumping problems and always label the bottom 0. Simply because I'm thinking about these examples where you don't have a choice. So at some point I was like, let's just do them all that way. Even if sometimes it's slower. It just changes the one little tiny thing. But you get the same answer. So now we're going to look at a given slice at a given y value. Now what could y be? This is the first observation. Y can only be 0 to 5. That often confuses people because they think, I thought you were pumping it to the top. We deal with the distance lifted separate from the value of y we're starting with. So the bounds are always going to be where your water, what y could be. In this case, where your water starts. And we're trying to find the distance lifted. So that's going to be 10 minus y. All of this together I feel like works as a unit, meaning if you plug in 0, you can do a little test. If you take a speck of water that's near 0, any of the water that's near 0, it's going to be lifted 10. If you take a piece of water that's near 5, up at the top, all of that's going to be lifted 5. So I always can check this collectively to see that it makes sense. So if you did the bounds from 0 to 10, that wouldn't make sense because that would be saying some water got moved 0. Okay, and then we need the weight. So how much does this weigh? Well, it's going to be dy pi times the radius squared and then it's 62.5 pounds per cubic foot. So all we need is the radius, and in this case it's a constant. In the last problem it wasn't a constant, it was changing. It was 1/3 of y. So this is a fairly straightforward problem. It's going to be 62.5 times 4 pi, the integral from 0 to 5 of 10 minus y dy. And it would be a little easier to label the top 0 and the bottom 10, but if you did that, it would be the integral from 5 to 10 of x dx. And it turns out that both of these are correct, is what would have happened. But you can see the choices here depend on how you label it. Okay, this is going to be, what is 62.5 times 2? If we're going to do times 4, times 2 sounded easier in my head. This is going to be 5. Great. This is going to be 1250. So if you double it, is it 2500? Oh, not 1250. 125. So if you double, it's going to be 250. So it's 250 pi, and then it's going to be 10y minus 1/2 y squared from 0 to 5. And so it's going to be 250 pi, and then it's going to be 50 minus 25 halves, which is 20. So 250 pi, and then we're going to have 25 halves, and then 125 times 25 pi. Well, shoot, we're starting to get beyond what I want to do here. Maybe it's time for a calculator. This is not good use of the video's time. So 10, this is 12, this is 6, this is 0, this is 250. Zoom up because that might be where my head appears in the video. 1875 pi. 1875 pi foot-pounds. Let's check that out. I feel like there's lots of ways I could have made a miscalculation. This is fall 2009. Fall 2009, so way back when, right here. Solutions. Ooh, this was back when I used to write my solutions on paper. Uh-oh, something's off. What is off? So here I did the other labeling, but that shouldn't matter. I have a 75 here. Should that have been 75? Let's go take a look. Maybe we found a mistake. So when I plugged in a 5, it was 50, and then it was 25 halves. Oh, shoot. So this right here should have been 100 halves. So this should have been 75 halves. Oh, I did do a mistake. It wasn't in this multiplication, it was before. So it should have been 75 halves for a grand total of, after you simplify, 9375 pi. That's why I check. 9375 pi. I don't want the video to be wrong and people to be mad at me. Okay, but I want to focus on setup. A small rocket is blasting off from the ground. As it burns fuel, the rocket gets lighter. That's a leaky bucket problem. So that's different than a problem where you, at the beginning of the problem, all of these so far, at the beginning of the problem, you had a whole bunch of slices, and it was a bunch of small tasks. Same thing here. Same thing here. So I always think of all of those as a stack of books. And we're just figuring out the pattern to lift each book individually, and then we're adding them up. This is a different problem. It's just one object, happens to be a rocket, that's taking off. I don't draw these very well. And it's getting lighter or heavier. So at any moment in time, at some point the rocket will be up here, and it will have a certain force. And that will only go a small distance. So what we're thinking of delta x here is as the distance that force gets lifted. And then it's going to change, and we're going to do it again. It's going to change, and we're going to do it again. So in these questions, we immediately say, okay, we're going to think of the distance lifted as delta x, and then we're going to try to figure out what the force is at a given x, but they told us it. So there's nothing to do in these problems. It's just going to be 0 to 8, 40 plus 50 e to the negative x over 2 dx. This is the force. This is the distance each force got lifted. So when you integrate, it's going to be 40x. And if you've done my integration by parts lecture, we've talked about the shortcut for integrating this. So I'm going to use it from 0 to 8. Now the biggest mistake in the calculation, I remember when, I don't think I can remember when I graded this exam because it's so long ago, but was people typically plug in the 0 incorrectly. They assume that 0 is going to give you 0, which does happen here, but does not happen here. So this should be 8 times 40, so 320, minus 100, e to the negative 4. So all I just did was plugged in 8, and then minus 0, but the next one's not 0. It should be minus 100, because when we plug in 0, that's a 1. So it should be 420 minus 100 over e to the 4th, or you can leave it as e to the negative 4th. Let's see what mistakes I made on that one. 420 okay, there it is. That's it. So I just like to throw that in there as comparison. Notice where the distance appeared was right here. This was the distance. This was the force. So the overarching theme is we're trying to find the pattern for force times distance and add it up. Before I move to average value, let's pull open some other tests. Just click on a few. As we think about exam 2, I don't know why this is so big. But as we think about exam 2, the first 3 pages are going to mostly be integration on most of these tests. And so that's stuff we're going to be talking about in chapter 7. Then we get to improper is also part of that. Then we get to an average value question. Okay, so that's the stuff we've done. And then we get a pumping question. So typically the last page or 2 will have stuff that has to do with 6.4 or 6.5. We have, there's a volume question. We have done a little bit of volumes. There's a pumping question. So that's kind of just, it helps to see that. Okay, so let's just prepare in case there's an average value question. I like an example like this. The temperature on a given day object is this. Find the average temperature. So this is a fast application that's mostly meant as an integration problem. So since the bounds are 3 and 0, you would do this. This automatically would get you a few points. But the function we're integrating is this. And so I'm making this video, but at the time of doing 6.5, you didn't know how to do this. Not because of the average value, but because this requires integration by parts. But if you're watching this video, you've probably already seen my lecture on integration by parts, so let's do it. So that you can see that oftentimes I use average value just as part of another question. It's a small thing for me to ask, and then you get to show me your integration skills. Negative 1/2 e to the negative 2t. Let's do integration by parts. So there's going to be this 1/3. I'm going to leave a bunch of space. We're going to smush those two things together. So it's going to be negative 2t e to the negative 2t. If it was me, I would evaluate as we go, or you can wait till the end. Remember, the bounds don't change. So now we're going to put these two things together, so it's going to be minus the integral from 0 to 3. And when you put those two things together, you get negative 2 e to the negative 2t. And this is what integration by parts does well for us. So this is going to be 1/3. This is going to be negative 6 e to the negative 6 minus 0. And this one is 0 because of that. And it's going to be plus because of these two. But then when I go to integrate, it's going to be e to the negative 1/2. It's going to be like this, e to the negative 2t. And then we're evaluating that from 0 to 3. So all together we have 1/3 negative 6 e to the negative 6 plus negative 1/2 e to the negative 6 and then minus negative 1/2. Here e to the 0 is 0. There's nothing else in there. So it's 1/3. We could distribute the 1/3. I just was been waiting to see if I could simplify before I do that. Plus 1/2. Not much you can do. You can clump these together. So maybe before I distribute, I'll write this as negative 12 halves minus a half, e to the negative 6 plus a half. And then putting it all together, that's negative 13th. Let's do it in 2 steps. If I was doing this myself, I might have skipped a step there, but I don't want to do something too quickly. Negative 6 plus a half. And then maybe we'll... Actually, a online calculator would factor out the 4 because it's going to look prettier. So this would be 1/12 negative 13 e to the negative 6 plus 2. I factored out a 4. So many ways you could write it. I'm happy with any of these. Okay, so let's look at that. That's winter 2015. Winter 2015. Zoom out a little bit. Let's look at my solutions. Got some integrals to do there. Some things we haven't done yet, and then you get this average value question. Oh, something looks off here. Why is it a little different? Did I not copy a 2? Oh, maybe I didn't copy the 4. No, I did. There was this 4t. But I don't think my answer is equivalent to what they wrote. So let's see if we can find... Now we're going to play the game of how do we find a mistake if we think there is one. So I put these 2 things together. This was minus 2. I integrated, this was minus a half. I plugged in 3. And then I plugged in 0. Ooh, I don't see it. Let's look here. Negative 2. Let's do a little side by side. Usually I can spot it, but this all looks the same. Yes. Next line. Yes. No, I see it now. Hopefully you spotted it before me. I did not bring this down. I got rid of the negatives, but this should just be negative 1 because the 2 and the 1. Oh, so that makes it a whole lot nicer. So I wasted a bunch of time there. Sorry about that. Let's fix this. You can see I always was a student that was prone to small errors, but I sort of learned how to check my work and reduce those. That's part of what you're going to be doing. So I always made small mistakes on tests, but I got better and better at learning how to check things. This is a little harder to check, so I might have just lost a point. But it's much nicer, I see. I should have recognized that something was amiss when the numbers weren't coming out very nice. Because on a test, I wouldn't have probably made it come out like that. Let's go look here and see. Yay, we got it. All right, let's do one more. So here's an average value question where I tried to make it kind of more interesting. I picked out a function that sort of was reasonable and said, if you study X hours, here's the score you're going to get. So if you study 4 hours, you get 80%. We're not going to argue about whether this is accurate or not. This would only be accurate for some students and not for others. But if this is the correct formula, then a natural question is, what's the average temperature you might expect if the students are studying between 4 and 10 hours? Okay, so let's do it. So the question is 1 over 10 minus 4, the integral from 4 to 10 of 100x over x plus 1 dx. And so that's going to be 100 over 6 or 25 over 3, depending on how you want to write it. But the challenge is going to be, how in the world do you integrate this? The truth is there are many ways to integrate this. You could do a substitution. You could do a division. Once we get to section 7.4 and we talk about partial fractions, I think more students would think about division because you can do long division this way. If we haven't done that lecture yet, then this is going to look weird. But it works out really well. It's 1. Sorry, what am I doing? Better do long division correctly. The denominator is x plus 1. This is x. Goes in there once, and then you subtract. You get a negative 1. So this is just one of many ways that you could rewrite it. Whenever the power on top is equal or bigger, you can always divide and simplify to something equivalent that's reduced. That's part of a small thing we're going to say in 7.4. A textbook would always do it this way. They would write x plus 1 minus 1 and then realize it was this, but that's really kind of clever. The other thing is you could do u equals x plus 1, and that'll work too. But the easiest solution in my mind is to do the division. And once we've done 7.4, that'll be something you would think to do. At that point, then we can just straight integrate it, because it's going to be x minus, and this actually this is the log of x. It's a part of the more generalized formula I gave. And then you're going to plug in a 10 and a 4 everywhere. So 10 minus log of 11. So you don't really need those absolute values. Minus 4 minus log of 5, because all the numbers are positive. And so it's going to be 25 thirds 6 minus the log of 11 plus the log of 5. And we could play around with that all day, but that was that number. This was fall 2009, so let's pull that up. Fall 2009. Yeah. So it was 86%, almost 87%. So if you took the people that studied between 4 and 10 hours, their average score. Okay, so how many hours would she need to study to get exactly the average score? So this is this idea of if you have a function and there's an average and the function's continuous, it'll have to hit it. So in other words, this must hit this. This 25. This is a awful question. Did I really ask this? I didn't realize. Oh, it is. If you got stuck on this one, I think this is something I asked as a decimal question back then. This is from a long time ago when we used to do more stuff with decimals and we allowed more stuff with calculators. But if you don't, it's kind of a mess. So right now I'm going to put mess here. And by mess, I'm going to mean this thing. And then I'm going to solve. The way you would solve something like this, and this was not intentional. I'm probably going to remove this problem for future quarters. But it's solvable. You would move this over to the other side. You get 100 minus mess times x equals mess. So the final answer, and this is actually how I would do. I wouldn't label it mess. I would give it a symbol. But if I had to solve something like this, this is what I would do. And so I get x is this number over 100 minus this number. So that was just a little messier than I intended. Again, I probably wouldn't ask that because the numbers are pretty gross. But you got to study about 6 hours. We used to emphasize that piece. There was more we did with average value, so now I remember why I might have asked that, but I wouldn't put too much worry into that. Okay, so lastly, to finish up, let's go take a look at the exam archive. Click on a few other ones. Here we go. Integration, 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 integration. That's the stuff we're focusing on section 7.1 through 7.5. Simpson's rule, that's 7.7. We haven't learned that yet. Improper integrals, that's 7.8. So you can see pretty confidently that probably the first 3 pages, maybe even the first 4 pages, will be on chapter 7. But very likely the last page will be on chapter 6 in some way. So here's a pumping problem that looks scary, but actually isn't too bad once we read it. This one, just looking at a few exams, integration, average value, then approximating, but you'll set it up. Arc length, we don't know yet. That's 8-1. I don't know if that'll be on our test yet. And then we have a cable, pumping. All right, hope that helps.